and welcome to this XP Solutions XP Live webinar. My name is Jessica Jeffries and I am a Products Manager here at XP Solutions. Today's webinar is the second in our 2D webinar series and is titled Modelling Structures in Floodplains. And this is part of our 2D modelling series. The webinar should be useful to you whether you're new to 2D modelling or looking to get into the details of the theory, setting up and running models. We'll first run through a presentation and then there'll be a software demonstration. Now I'd like to introduce today's presenter. We're lucky enough to have Bill Syme from BMTWBM join us again today as our guest presenter. And Bill has 25 years of experience working on riverine, estuarine and coastal studies, of which most have been in the flood hydraulics field. He's successfully managed and led a wide range of flood studies, both in Australia and overseas. And Bill is also the author of the XP2D engine. Today, Bill manages software operations at BMTWBM and provides specialist flood modelling and management advice. So I'll hand you over to Bill. Welcome, Bill.
Thank you, Jessica. Hello to everyone. Good morning, good evening, good afternoon, wherever you are. Today, I'm going to focus on discussing how you go about modelling structures in floodplains and rivers and creeks from both a 1D and a 2D perspective with a strong focus on the 2D. I'm going to cover a few fundamentals in the first slides and then we'll focus on looking at some examples through bridges and culverts. And finally, the other type of sort of structure you might find, of course, is in urban areas, how do you treat buildings and fences? Following that, Jess will give a model demonstration and then we'll do the question and answer. So, with structures, there's a lot of energy can get dissipated, and effectively what's happening there is as water changes its speed and direction, it loses energy. And this is very much in addition to the energy dissipation from bed friction. So it's an additional loss that occurs besides your Manning's-End roughness. This is really only pronounced at bends, sharp river bends, not gradual ones, but sharp river bends, flow constrictions, which of course are bridges, culverts, anywhere where the water is forced to contract and then expand. Generally speaking, the energy lost is a proportion of the kinetic energy component, and it's very dependent on the speed of the water as it changes, speeds up then slows down. If your velocity through a structure is only 1 meter per second, you've really only got about 5 centimeters of dynamic head that you can lose. If it's 4 meters per second, however, the kinetic energy being proportional to V squared, you've got nearly a meter of water, 0.82 meters of water of kinetic energy that could be potentially dissipated. So just to demonstrate these form losses and how there's a very big fundamental difference between a 1D scheme or 1D equations versus the full 2D equations. So here on the left you can see a little model which is of a right angle bend, and if we make a little 1D model of that setup, essentially we end up with a profile that looks something like that, and it's basically following Manning's-End equation. And as far as the 1D model is concerned, there's nothing, it doesn't know about that bend. You could bend to the left, it could bend to the right, it could go straight ahead. It just doesn't know that that bend exists. If we make a little 2D model and look at and generate some flow patterns, as you can see on the right, the flow deviates from being just normal flow to being a more complex flow arrangement. And the red line is the water surface levels going down the profile on the left. At location A, you can see that there's a mounting of water, and that's because the water is slowing down and kinetic energy is converted to potential energy and the water level rises. And you can see that in the red area on the far right. But importantly, the upstream water level, the water level that's driving the pushing the water through this little right-angle bend is higher. And that is one of the fundamental differences between a 1D and full 2D equations, is that they will lose energy where the water is forced to turn or to change speed or so forth. So at a structure such as a bridge or culvert, the general approach that we take for modelling in 1D is that we specify entrance and exit losses, and many of you will be familiar with specifying those. It's very easy, of course, just to take the default values, but in truth, these losses actually do vary depending on the flow conditions at the time. And depending on the software you're using, you can trust the software to estimate these values. Some users like to force these values, but effectively, the bigger the change in velocity through this structure, so if you go from very still water to fast flowing water through a structure to very still water, you'll get greater energy losses than you will if the velocity is maintained to some extent. The other challenge is that these losses can vary significantly with the height of the water as the flow conditions change. So 1D is very much an approximation to the energy loss through a structure, and as modelers we have to be very aware of that. For example, at a bridge it gets even more complicated. Many of you would probably be familiar with the Hydraulics of Bridge Waterways publication and other documents, and you can develop loss coefficients for different water level heights based on the contraction and expansion due to the embankment. Piers will generate a small loss depending on their size, and even factors such as eccentricity, skew, whether there's one or two bridge structures, and then when the water hits the deck it gets even more complicated again. So it's not a simple process to set up your loss parameters for a bridge without having a good understanding of what's going on. When you move to modelling a similar constriction in using the full 2D equations, you actually don't specify any entrance or exit losses. And this is because, as I mentioned before, the 2D equations will simulate the speeding up, slowing down, any eddy formations, any change of direction. All those things will dissipate kinetic energy, and the 2D scheme makes a much more accurate attempt at simulating that than a 1D scheme. And this all implies that there's no need for entrance or exit losses. But is that really the case? For example, if you had some bridge piers in here, generally speaking your 2D resolution is way too coarse to simulate any sort of fine-scale losses from those bridge piers. And research is even showing that if you make this mesh so small that you can, even that's not correct due to other factors. You really need to move to CFD modelling. And what about losses in the vertical? So when the water hits the bridge deck, there's energy dissipated, and that needs to be accounted for in some manner. So what we tend to find is, even with the 2D schemes, while the flow patterns might look much more accurate and it's a much closer step to reality, you still may need to account for these fine-scale losses through additional energy losses. So it's very important as modelers that we're very tuned into this. Let's look at a simple example. Here we have a small culvert and a little 1D model pushing water through that culvert. The approach velocity is about 0.7 meters per second. The velocity through the structure is 2.9 meters per second, and the departure velocity is 0.8. And if you do some desktop calculations and theoretical, using theory and empirical formulas, you generally end up with an entrance loss coefficient of around 0.38 and an exit loss coefficient of around 0.55 for this setup, with a head drop of a bit over 0.4 of a meter. And the profile you get from a 1D model is something you can see there in the bottom right of the screen. Let's look at what happens when you make a little 2D model of that same setup. what occurs is that you get a sort of nicer flow patterns, as you can see at the top right. There's even a small eddy forming. And the water surface along the top line through there sort of shows the water level rising slightly due to kinetic energy being converted to potential as it drops through the structure. But the upstream water level is effectively too low. And so the 2D scheme is doing a reasonable job of modeling the energy losses through there without specifying any entrance or exit losses, but it's still not sufficient. And that would be, once again, due to very fine scale losses, particularly in this case due to the vena contracta, which that resolution cannot model. So you may well need to calibrate or adjust these structures when they're being modeled in 2D by adding additional losses. And typically for this arrangement we find an adjustment of around 0.2 of an energy loss, which you can apply to your structure, is sufficient to give you the right sort of afflux. So when you're modeling these structures in 2D, the types of things that you can do is to put a lid on the cell, which effectively, such as a bridge deck, which means that your flow area remains constricted to that below the lid. You can apply additional energy loss once the water starts to surcharge against the deck. Plus you can apply an energy loss through the water column for bringing piers or other small fine-scale losses. You can partially block your cell sides. And as mentioned, if you have a pier, you can apply additional losses. So there are types of things that you can do to your 2D elements for the bridge and floating deck options. Another option is that you can actually layer or vary in height your energy loss and blockage. Up to 3 layers can be specified. The fourth or top layer is always assumed to be unblocked. So for example, on the right here, we may have bridge piers through the first layer, and they might have a small blockage and a small energy loss. You then have the bridge deck, fully blocked, handrails, partially blocked, and then the rest of the flow is at the top. And what the 2D scheme is doing here is that it's lumping those, depending on the water height, it lumps those parameters together to give a overall sort of energy loss and blockage. And that can give you a good representation of a structure, or even something as simple as a pipe crossing a waterway. Importantly, you can actually also vary the depths of the layers and the elevation of the inverts spatially. So if you have an arched bridge or some unusually shaped structure, or if your bridge deck is not exactly horizontal, you can set that up quite easily in the interface and model that situation. So in specifying these losses, you do need to look for the literature, and if you have any calibration data for guidance. Documents such as hydraulics of bridge waterways is commonly used to generate pier losses and other types of losses, but you do have to be very focused that generally 2D schemes will model the contraction and expansion losses quite well. They're just not going to pick up the fine scale losses. Another good practice is to compare with other software such as HEC-RAS, but you do have to be very conscious that it is just another model, another approximation, and if it is a very tricky or complex structure, the more ways that you look at estimating the afflux and losses and checking your model, the better. It's just very important to note that these structures is effectively a complex 3D problem, and we're trying to simplify it down to a 1D or 2D solution. One point of note that Jessica will probably mention is when specifying energy losses on your 2D flow constrictions, if your flow constriction is digitized as a line or polyline, you just put the full value. For polygons, however, you put a loss per meter in the direction of flow. And the reason we've done that is that this means that that element or that flow constriction is independent of cell size. So if you change your cell size from 20 foot down to 10 foot, then you will not have to change that setting. The objective with all this is very much to be independent of cell size. Let's look at an example. On the left we have a 1D, 2D model. So we have 1D links, nodes, and there's a bridge structure there with the yellow arrow in the middle. And on the right we have a fully 2D. Well, in fact what we've done is we've transitioned from 1D to 2D in the bottom right of the screen, and the rest is just fully 2D. And the brown area is a layered flow constriction. At the 1D bridge on the left, or the layered flow constriction on the right, you can enter in parameters that define the shape and losses and anything else that you need to specify to model that structure. And in this case we're running with recommended values. When you run those models, you get these results. On the left is the fully 2D and on the right is the 1D 2D. So on the left we have the fully 2D image, and you can see that the flow patterns are quite nice compared to the ones on the right where you have a 1D approximation in here. But interestingly, both these models give a very similar afflux, which is in accordance with what we would expect. And the black lines are water level contour lines, so you can see that there's not a lot of difference, except maybe around where the 1D area is. You'll see some slight differences, but generally speaking, the water levels either side and out on the floodplain are very, very similar, which is, of course, very encouraging. And that's how those results came out. There was no reruns on that example. The other type of situation you might have is just a simple culvert through an embankment. And just a few tips if you're doing that situation is the number one thing to make sure of, or where people get unstuck, is that you just simply connect to a single cell on both sides. So if you have a very large structure or a bank of culverts that's 10 meters wide and you have 2 meter cells, and you just connect into one 2 meter cell, when that culvert is flowing at full capacity or even less than full capacity, that will cause problems because you're basically pushing 10 meters wide of water into a single 2 meter cell. So just ensure that if you select enough cells, as demonstrated on the top there, that your width of your 2D cells, and this is your wet 2D cells, so if there's dry cells in there, they're not included. The width of your wet 2D cells at various flow elevations is greater than the width of your structure. So you may need to use a line rather than just snap into a single point. The other common problem we come across is that the ground elevations in your DEM, particularly if it's coming from LiDAR or ALS data, they are often elevated above your culvert invert, and this will always cause problems. And the reason for that is LiDAR is often picking up ponded water, or there's just a lot of siltation. So always have a good look at your ground elevations in and around the entrance and exit to your culverts. They are the most common cause of problems such as instabilities at structures like this. Let's move on to modelling buildings. There's a number of ways that buildings can be modelled, and I'll just go through the three most common ways, I guess, that we see out there in the industry. The great temptation, of course, is just to simply block the building out. And what that does, as shown by this little demonstration model here, is the water is forced around the building, nothing goes through the building. In this case, some nice eddies are forming downstream, and the water realigns itself further down. And in this little example, the afflux caused by blocking those cells out is at around 0.137 meters. And all the water passes, 100% of the water goes around the building. Another approach is to actually digitize the building effectively on three sides, and normally leaving either the upstream or downstream open for water to get in. One nice thing with the XP2D is that you can actually raise the sides or the elevations on the sides of the cells, not the whole cell itself. And the efflux in this situation is 0.145 meters, which is slightly higher than blocking the whole building out. And for those who are very interested, the reason for that is that the water is coming into the building, and it's actually, if you look closely at the flow patterns, it actually works harder to get around the corner, or the upstream corner of that digitized wall. And so the separation is slightly greater, and that means more energy is lost, and you end up with a slightly higher water level upstream. As for totally blocking out the building, 100% of the flow goes around the building, and nothing goes through it. Another very common approach is just to specify a high Manning's N. In this case, I think this was a Manning's N of 0.3, and turning all those cells from 0.03 into 0.3 pushed the water level upstream to about 0.122 meters, so it's a bit lower than completely blocking the building out. 79% of the water flows around the building in this case, and about the remaining 21% goes through the building. And the velocity, this little model is based on a 1 meter per second velocity, so the velocity through the building is down to 0.38, and around the sides is 1.41. So they're the different, generally the most common approaches. There are other approaches, but they're the most common. When you apply that in the real world, you get these sorts of results. So in this slide, you can see the buildings have been digitized in and the cells deactivated, and this is on a 5 meter resolution. It doesn't give too bad a representation. You can see in the top part of the image here, we've intentionally not modified the building. So you see the water just going straight through those buildings because there's been no change to the model to even try and represent those buildings. Whereas in the lower part, you can see the flow trying to work its way around the buildings. Of course, if you move to a 2 meter resolution and longer run times, you get a much nicer result. But once again, a very good comparison at the top where there's no building representation, and at the bottom where there is. So if we move to something where we're blocking 3 sides of the buildings, what that means is water has to go around the buildings, but it can still get into the building. So your storage effects are modeled. In the previous example where you're blocking the whole cells out, you're actually also removing the storage from the system, which may or may not be what you want to do. And if storage is important, then an approach where you're just blocking the sides of the elements is preferable. Once again, this is on a 5 meter resolution. If we move to a 2 meter resolution, you get similar flow patterns to what we have with the inactive cells, with the water being pushed all the way around the houses, but importantly, the houses are also being shown as flooded. You can, of course, raise the elevations as house pads. So, for example, if these are slab-on-ground houses and they're 0.3 meters typically above ground level, you can actually modify the ground elevations to represent that so that they only flood once the water gets to that depth. It's also important to look at your results. As you can see here, over here we have an example where the flow is going through the building, and that's most likely because the elevations applied to those cell sides were not set. So you do have to raise the cell sides. You have to digitize your line and then basically put a very high elevation so that water never goes across that line. The third option was modeling as a high roughness, a high Manning's N value. And at a 5 meter resolution, you do get some differentiation between a bit faster flow between them, but not as much as maybe we would like. When you go to a 2 meter resolution, it's a bit more pronounced, and maybe these buildings need to have an even higher roughness. But the advantage of using a higher roughness is, of course, if your grid resolution is too coarse to represent the gaps between the buildings, then you really have no option other than to use a high Manning's N. So just on the pros and cons of the different building approaches, inactive buildings are very tempting, very sort of not necessarily a common way, but people would like to do it that way. But the important thing to recognize is that you do not include the storage effects. And your grid resolution has to be fine enough that you can represent the flow patterns between the buildings and other structures. If you digitize a building that is being closed on 3 sides, there's different schools of thoughts whether you should leave the upstream side open or the downstream side open. If you leave the upstream side open, your water level in your building tends to be higher, so people often favour that because it might be a bit conservative, although some believe that the water level in the building should be more reflective of the downstream side. Yeah, of course, as I mentioned, you can raise the building if it's slab on ground construction. You can raise the ground elevations, and that house or building or that will not flood until that water depth has reached that the amount that you've raised it. And most important is that your storage effects are represented in this scenario. The high Manning's N option is quite common, partly because it's probably the easiest to do, and certainly if you are provided with a building footprint layer. It's also a good option for your coarser grids, but it may not give you the complex flow patterns you might need if you're drilling down to a very fine resolution. If you're using direct rainfall to apply water to your model, you do have to be aware of a few key points. Inactive cells, or when you block the whole building out using inactive cells, they do not receive any rainfall. Therefore, either you don't use that approach for modelling buildings, or in some cases I have seen modelers adjust the volume of rainfall so that it compensates for not being applied to the buildings. If you are using the high Manning's N approach on buildings, you have to be a bit careful, particularly where the buildings are outside the floodplain, as the direct rainfall can tend to mound or build up on top of those buildings because it finds it hard to escape off the building surface. What has been done by a number of studies is to actually vary the Manning's N with depths for buildings. And the approach here is actually quite interesting, is to apply a very low Manning's N for your very shallow depths, and that means that the water will run off those buildings. When the direct rainfall is applied to those buildings, it runs off very quickly, such as off a roof. However, if the flood depths build up around that building, that normally means that the building is in a flow path or in a backwater area, and it becomes an obstruction to water. So you transition to a much higher Manning's N for depths, let's say above 0.1, 0.2 meters. Modelling fences. As we showed before with blocking the building size, you can actually change the elevation of your cell size, and modelling a fence is done in the same or similar manner. You do not have to adjust your whole cell. So these cell sizes can wet and dry, and you can actually vary your parameters such as blockage and losses with height by using the layered flow constriction feature. You can actually also collapse your fences based on a water level difference or a trigger time or even just a straight water depth. And the 2D scheme will handle both upstream and downstream control flow regimes. So when the water is upstream controlled, it uses a weir equation, and when it's downstream controlled, it uses the full 2D equations. This is just we've digitized a fence in this little area here on the screen, which then breaks and it's like a little mini dam break. I'll just demonstrate that through. So as the waters will come down, they'll reach this area here, which is in the circle before. It will then burst, the fence will collapse and then burst through the buildings here. So there, it's collapsed, and now the water is pouring around these buildings in a dam break type scenario. And blockages. I'm not sure about elsewhere in the world, but here in Australia, this type of handrail is actually recommended as it doesn't collect debris. But whether that actually works in reality has been proven not to be the case. And so a lot of agencies these days are very much specifying that rails are model blocked or partially blocked. And to do that, we can use our layer flow constrictions if you're using the 2D approach. And we're still working on how to model these cars. That's probably a feature for an upcoming release. I'll just finish off with mentioning the AR&R Project 15. This is available on the internet, and Jess can send people the links to this document. It provides, it's a couple of hundred pages, and it provides guidance on many, many topics related to 2D modeling. It's been formulated over a number of years, and it's a great reference for those who are keen to learn more about 2D modeling. A couple of relevant chapters that we've addressed today in this webinar is section 10.10 on structures, how to deal with those, and section 10.11 for buildings and fences. But there is much more in this document for those who are interested. Well, thank you for listening to the presentation. I'll now hand over to Jessica. She'll give a live demonstration.
Thanks for that, Bill. Well, great to get the theory, but what I wanted to do was show a little bit of the practice. And I'll start off with our 1D bridge model. So this is the model that Bill showed the results for in his slides. And those of you familiar with XP might recognize that this hashed section is all blocked out in the 2D because that's what we've represented in the 1D model. If I turn on the nodes and links here, we can actually see that 1D model, and in particular of interest, we're going to have a look at this section here, which is the bridge. Now, if I zoom in, you can see we've got a different actual visual representation of this link here, and that's because we actually have a bridge link available in the software. That's available on the right hand side on our toolbox as a bridge, and this has actually been set up that way. And what that means is when we edit the data, we don't have lots of options to choose from. We just have the things relevant to a bridge. So you can see the bridge length and elevations and so on are on this first screen. Our weir coefficients for when we have overtopping of the bridge, and then if we go into the edit section, we have our usual cross-section data. And what's particularly useful here is if this bridge has multiple openings through the underneath side, if we have piers, for example, or if we have culvert sections, we can actually add those all in this one location. So if I click on the edit option here, you can see that we've included a pier, and this is where we would also specify the losses needed. Obviously, Bill talked about the losses needed in 1D models for our bridges, and we can put in the entrance and exit losses here. We could also change this or add additional sections if we wanted to model a culvert. So that would be very easy to set up. We could right-click on any link and actually change it to a bridge link, or use our usual method of actually drawing on the screen there. And obviously you've seen the results there, which have been run on this model. If I just animate those, we can actually just move through and see how the velocities and the water depths are changing as we run through the animation. So that bridge is definitely you know, part of the restriction here as well as the road. I'll switch over to the 2D model with the flow constriction now. So as Bill mentioned, we had the channel coming down in 1D, it then converts into a fully 2D scheme, and rather than using a 1D link here, we've used the flow constriction option. So the way we'd set that up is in the 2D layers. So on the right hand side we have our 2D model section, and there is the option to add a flow constriction layer. That's how we'd include that one. Then within the flow constriction layer we have the option to draw a polyline or a polygon. We also have the option, as with our other 2D layers, to actually import from GIS. So if we had multiple things to represent here, we could import them. Otherwise we can just use the drawing tools that we're familiar with to actually draw in this shape. If I click on this and edit the data, it's worth just showing that this one has been set up as a layered flow constriction, but we also have the option for a bridge deck or floating deck. So the bridge deck might be used where it's a simpler bridge, where we don't have a railing above, for example, where we don't have piers to include. We might use the floating deck for something like a weir on a river or a pier that's would float on the water. The layered flow constriction has a lot of different applications, bridges, fences, even buildings. So it's important with the energy loss that we are conscious of whether we're using that polyline or polygon, with the polygon being a loss per meter, as discussed by Bill, so that if you change your cell size you don't have to change the losses associated with it. So in this example these losses are losses per meter, which is why they may appear a little different to what you would expect. But this shows we've got our 5% blockage below the bridge deck, if you like, in the first layer, and the levels there are set up for the invert, essentially the underneath the ground, if you like, under the bridge. We've got a constant deck level there, the obvert of that layer, and then when we go into layer 2 it's blocked out for 2.1 meters, 100% blocked with a higher loss, and once we go into layer 3 the blockage is less, to represent the fact that some water will get through the railings for about a meter or so. So that's how we set up these flow constrictions, and again we can have a look at those results that were animated, shown by Bill, the sort of maximum results, and actually see the water passing through this flow constriction, but being manipulated, if you like, by the changes we've made to the 2D cells there. So that shows you a little bit about how the bridge models were set up. Although we don't have a 1D culvert in this example, I will just show you how you could change the interface lines. So if we were to have, if I turn on the links and nodes here, if we were to want to model a culvert just by drawing a link, then what we could do is, if we were linking this culvert to 2D, then in the node we would set link invert to 2D if it's a culvert going underneath a road embankment, and if this culvert was wider than our grid cells, So say we had 10 meters of culvert here, we would add an additional interface line just by drawing a polyline that matched up with the width of the culvert there and connect that into our node. We only need one connection point there, which we can draw with the snap tool. And then the important thing is that we actually change this interface line from a head interface line, which is typically used for open channels, links between 1D and 2D, to a flow interface line. So that would be how we would set up a culvert scenario in the floodplain, linking the 1D and the 2D. So moving on to our building examples. And the first option here, we've got the inactive area option. So again, we can have a quick look at the results and just see in a bit more detail how those velocities are actually changing, how the water moves around the buildings here. I've got the 2D 2-meter grid, animating here. You can see we've got some of our 1D nodes spilling as well as the main wave of water coming through, and we can see it nicely curving around the buildings here. One thing with this method is it is very easy and quick to set up. So these inactive areas are actually brought in on a layer here, either by GIS if you already have them digitized in another format, or we can also do this manually. So for these houses up here, if we wanted to add those into the model, we could just draw them in and add as many houses as we wanted to include. So pretty quick and easy to set up, particularly if you can import by GIS. Moving on to our option with a high Manning's N value. This is probably about as simple to set up as well. We'll just have a quick look at those results playing through as well. And again, you can see the water can go through the buildings, but we see this reduction in the velocities, in particular in this 2-meter grid example. Over here, you know, we've almost got hardly any flow through the building. And again, this can be quick to set up by importing the buildings into a land use layer using GIS, or again using our drawing tools to draw those. Once we've got those in the layer, where we make edits to the layer is in the global database. And our 2D land use section, if I just go into the buildings layer, you can see that we have a Manning's N of 0.3 set up for these buildings. If we wanted to take the approach that Bill mentioned, we can set a depth and a roughness so that we have a lower Manning's N value for shallow depths and a higher Manning's N for deeper water. And we could also add under the topography layer, we don't have a model, but the fill areas option if we wanted to take account of the pads, the ground that the building is on if it's a slab structure. Final buildings model we have, which is wrong model there, sorry, which is worth having a look at, is the option where we've digitized just 3 sides of the building here. So it's a little bit clearer to see if I just briefly turn off the background image for you there. You can see that the gap means that water can get into the building, and we can show that the building is flooded. This particular model's been set up with the downstream side of the building open. So what we see as the water approaches is that the velocities around the building look very similar to them being blocked until we get around the back, and then the water's able to sort of get in behind those, behind where the gap occurs. And in this case we have set these up as ridge lines, and so they are under our topography layer. And if I edit the data here for one of them, we've just used the offset option to change the elevations by 3 meters to account for the height of the building. And we have a little visual display there to show you what's being done. So that covers our buildings. The final model to show is the fences there, which I just had up before. So the green line in here, again we've got a ridge line in here to show where the fence is, and that's been set up to hold the water back. But what we see is, because of the way this fence is located, we get a big build-up of water in the center of the screen there. And so we've modeled a breach using the dynamic elevation shapes. So if I turn on this layer, you can see that we have this section is going to be edited by the breach. And the way we actually the way we set up that breach, if I just select that and edit the data, is with a trigger. So we're actually looking at a change in water level either side of the fence there. But there's a number of different ways to do this. So just to show you that animation occurring again, if I just step through this, you can see the water approaching here. We get a bit of a build-up of water. Obviously it doesn't take long, and then it spills through on the other side. So this can be used not just for fences but also walls. In fact, this is most likely more representative of a wall, but also for levee breaches and other applications. And the way we included that animation in the PowerPoint, in case you are producing these models, is just by using the record button down here. So this allows you to record any animation in your model and save it out, and obviously include it in a PowerPoint presentation. So I'll go back to that PowerPoint. I'd like to just thank you all again for joining us for this webinar, and just make a final thanks to Bill here as well for giving up his time to share his knowledge with you.